Hi, in this module, I'm going to talk about probabilistic programming, a new way to think about defining Bayesian networks through the lens of writing programs. And this really is going to highlight the generative process aspect of Bayesian networks. So recall Bayesian networks is defined by a set of variables. There are directed edges between the random variables that capture qualitative relationships. Then for every variable, we define a local conditional distribution conditioned on the parents of that variable. You multiply all these together and you get the joint distribution over all the random variables. And then given this joint distribution as a probabilistic database, you can go and do probabilistic inference and answer all sorts of questions. So what we're going to focus on today is how to write down this joint distribution or via the Bayesian network. So we're going to look at it via the lens of programs. Let's go through this example. So let me write a short program that I claim is going to be equivalent to writing down either this equation or drawing this graph. So here it goes. So first, I'm going to draw B from a Bernoulli distribution. So you can think about this as the Bernoulli is just a function that takes an epsilon and returns 1 with or true with probability epsilon. So B is going to be set to 1 or true with a probability epsilon. I'm going to independently do the same for E. And then finally, I'm going to set A equals B for E. So if I run this program, it's going to produce a setting to A, E, and B. So in general, a probabilistic program is just a randomized program such that if you run it, it sets the random variables. And in particular, it produces an assignment to the random variable. So while you can run the program, it's useful to think about the program itself as just a mathematical construct that's used to define a distribution. In particular, the probability of a program producing a particular assignment is going to be, by definition, the joint distribution over that assignment. So let's look at a more interesting example that showcases the convenience of using programming. So this one's going to have a for loop in it. So let's say we're doing object tracking. So we're going to assume that there's some object that starts at 0, 0. And then for each time step, 1 through n, I'm going to, with probability alpha, I'm going to go right. So I minus 1, x I minus 1 is a previous location. I'm going to add 1, 0 to it. I'm going to go right. Or with probability 1 minus alpha, I'm going to go down. Okay? So here is the Bayesian network corresponding to this probabilistic program. So you can see that each xi depends only on xi minus 1. So the cool part is that this is a program, and we can actually run this. So this is implemented in JavaScript behind the scenes, and you click run with alpha equals 0.5, and each run produces an assignment, x1, x2, x3, x4, and so on, to the random variables, and we can visualize them. And you can play with alpha. If alpha equals 2, then actually let's make this 0.1. Then I actually need to press Control Enter to save. So if it's 0.1, then all the trajectories are going to be over here. If it's 0.9, then the trajectories are going to. Okay. So this program specifies what is called a Markov model, which is a special case of a Bayesian network where we have a chain. Each variable is only dependent on the previous variable. So with this Markov model, we can ask particular questions. For example, what are the possible trajectories given the evidence x10 equals 82? So here, I'm going to condition on x10 equals 82. And if I run this, then I'm sampling from all the program traces where I restrict only those ones where x10 is clamped to A2. So this is a way to visualize the conditional distribution of a probabilistic program. So now I'm going to quickly go through a set of examples of Bayesian networks and by using probabilistic programs to write them down. So this is going to be a fairly broad and quick overview. So one canonical application is in language modeling, which is often used to score sentences for speech recognition or machine translation. So here is a probabilistic program. For each position in the sentence, we're going to generate a word xi given I minus 1. So this is actually in NLP, it's called bigram, or more generally n-gram model. So here we generate x1, maybe that's rec, and generate x2 given x1, maybe that's generate x3 given x2, that's nice, and x4 given x3, that's beach. So here is an example of object tracking, which that's actually we're going to study at length in future modules. This is called a hidden Markov model. So here for every time step, t equals 1 to big T, I'm going to generate an object location ht. So for example, h1, I'm going to generate 3, 1. And then I'm going to also generate a sensor reading et given ht. So given h1, I'm going to generate e1, and I might get something like just the sum of the coordinates example. And then I'm going to move to the next time step, generate h2 given h1, maybe that's 3, 2. I'm going to generate a sensor reading, which is the sum of the coordinates, and then so on, generate h3, generate e3, generate h4, e4, generate h5, e5. Okay. So that specifies the joint distribution over these object locations and sensor readings. And now a canonical question you might want to ask is, given the sensor readings, where is the object? So here is a generalization of the HMM to allow for multiple object tracking. It's called a factorial HMM. So here for every time step, now I'm going to have two objects, A and B, and I'm going to generate the location of object O at time step t. For example, here I have H1A and H1B. And I'm going to generate a single sensor reading, which depends on both the objects. So here I have E1 conditioned on both H1A and H1B. Go to the next time step, generate the object locations for the two objects, and then generate the sensor reading conditioned on those two objects. Transition to the third time step, generate the sensor reading, transition to the fourth time step, generate the sensor reading. So in general, this defines a joint distribution now over all the object locations for both objects, as well as the corresponding sensor reading. So here is another classic example called naive Bayes, which is often used for a very fast classification. So the way naive Bayes works is that we're going to generate a class or a label, y. For example, in document classification, I might generate that this document is going to be about travel. And then for each position in the document, I'm going to generate a word wi. So for this one, I might generate beach. The second word might generate Paris, and then all the way up to wi. So now the typical way you use these naive Bayes models is that you're given a text document, which is the sequence of words. You ask for the label. What is this document? So a fancier version of the naive Bayes model is called the Latent-Dirichlet allocation. And here we're going to assume that a document is not just about one topic, but possibly multiple topics. So I'm going to generate a distribution over topics called alpha. Notice that this is actually a continuous random variable. A might take on values which assigns probability 0.8 to travel and 0.2 to Europe. And then for each element in the document, each position I, and generate a topic zi. So here I might generate travel for z1. And I'm going to generate a word given that topic. So here w1 given z1, I'm going to generate the word each. Then move on to the next word, generate a topic, generate a word given that topic, and so on and so forth until I reach the end document. Okay, so the typical way you use LDA is that you're given a text document, the words here. What topics is it about? I want to infer what are the topics for each of the words, but also the topic distribution for that. So here is another example which generalizes the Bayesian network that we actually saw in a previous module. So in general, let's suppose that you have a bunch of diseases. We're going to generate for each disease DI, which is the activity of disease I. So we might have pneumonia, generator 1, cold, and malaria. And we're going to have a set of symptoms where each symptom we generate an activity of that symptom, SJ. So we might have fever, which depends on the diseases, and we might have a cough, which depends on a set of diseases, and we have vomiting, which depends on the diseases. So now the way you typically use this Bayesian network is that a patient comes in and reports some symptoms. You ask the question, what diseases might they have? And I'll just point out that this is a case where missing information can be handled naturally. If a patient doesn't have, if you didn't record a particular symptom, then you can just kind of ignore that variable. So here's another example. Motivation is that you have a social network and you want to analyze why certain people are connected with other people. So the model is formally called a stochastic block model. The idea is that for each person, we're going to generate a type of that person. So maybe we have 3 people, a politician, a scientist, and another scientist. And then for every pair of people, we're going to generate whether those 2 people are connected. EIJ is a Boolean to determine whether those are connected. So this politician and this scientist might be connected. There's a 1. And the generation of this only depends on the types of the 2 people in consideration. So 2 and 3 are scientists and they're connected. And this politician and this scientist are not connected. So remember, we are given the social network, which are just the connectivity structures. So these E's, and we're asked what is the probability of the people being of certain types. So that was a whirlwind tour of a lot of different popular Bayesian network architectures in the literature, but they all basically boil down to this one, which is that there is a variable or a set of variables H, which are generated first and then giving rise to a set of variables E. So the probabilistic program specifies a Bayesian network. By running it, it gives you a joint assignment, and the probability of producing that joint assignment is the joint probability. There are many, many types of models. I've only given you a very small subsample of them. But I want you to take away from this a general paradigm is that you come up with stories of how quantities of interest, H, generate the data that you observe, E. So this is really the opposite of how you normally think about machine learning or classification, where you start with the inputs and then you define a sequence of operations to produce the outputs. In Bayesian networks, often it's reversed. You think about the quantities of interest first, how they might arise in the world, and then how the data is generated from those quantity of interest. So this paradigm might take a little bit of getting used to, but it might become natural after some practice. All right, that's in